Welcome. Now we'll continue our goal of extending the natural numbers to more complex algebraic structures by introducing the integers. I'll consider some properties of the integers and what actual operations we're going to define on the natural numbers with some extended elements, such that we have a true ring structure. That is, we must add some additional elements that will provide inverses with respect to the addition operation, but these additional elements must be chosen so that the extension is actually a ring, namely as associative, commutative, and distributive. A convenient way of ensuring this is to construct the extension directly in terms of the natural numbers. Namely, we construct the Cartesian product n cross n, consisting of all pairs of natural numbers a and b that we write as a comma b. And we define the following operations on such pairs by the following. The sum of two pairs of natural numbers, a comma b plus c comma d, is pretty natural. It's a plus c comma b plus d. But the multiplication operation is a little more in depth, that a comma b times c comma d is equal to ac plus bd comma ad plus bc. It's pretty standard to verify that these operations satisfy the appropriate laws. The only slightly complicated case is with those of the associative law for multiplication and the distributive law, where we get a long multiplication where we see that a comma b times c comma d, all of that times e comma f, is this long expression in the middle. But if you factor that appropriately, we see that that's a comma b times a quantity of c comma d times e comma f. And additionally, we have the same thing for the distribution. We have a sum times a product is this very messy looking expression in the middle, but that turns out to be a product times a sum. I'm sorry, that turns out to be a sum of products. Once we have this, we can actually derive the integers by defining equivalence relations on the set n cross n, where we say that a1 comma b1 is equivalent to a2 comma b2 if and only if a1 plus b2 is equal to a2 plus b1. And we see that this is actually an equivalence relation by checking all the necessary qualities that equivalence relations must hold, namely reflexivity, symmetry, and transitivity. And we see that we can get the transitivity by if a comma b is equivalent to c comma d, and c comma d is equivalent to e comma f, then a plus d is equal to b plus c, and c plus f is equal to d plus e. So we add two terms, and we get a plus f plus c is equal to a plus f plus c by associativity is equal to a plus d plus e is equal to a plus d plus e, which is equal to b plus c plus e, which is equal to b plus e plus c, from which we can use the cancellation law, and we get that a plus f is equal to b plus e, so a comma b is equivalent to e plus f. And so we have a valid transitivity of this equivalence relationship. We have this immediate consequence that for any element a comma b, we have a entire equivalence class given by a plus c comma b plus c for any triplet of natural numbers a comma b comma c. And this is a very useful operation when we're dealing with this particular equivalence relation. We can also verify that all the group operations on n cross n preserve this equivalence class, in the sense that if you have any two equivalent elements of n cross n, then the sum is equivalent to the sum, and the product is equivalent to the product, in the sense that a1 comma b1 plus c comma d is equivalent to a2 comma b2 plus c plus d, and the same for multiplication. We finally get the integers, as we've been trying, by quotienting the Cartesian product n cross n by the equivalence relation we've just constructed. We call this set z from the German, and call this set the set of integers. In our construction, we see that the operations of addition and multiplication are well defined among these equivalence classes, so they're well defined on z, which is identified with n cross n quotiented against the equivalence relation. And these algebraic operations will satisfy the same laws as we wish. If we will recall that we can add things, we see that a comma b plus 1 comma 1 is equal to a plus 1 comma b plus 1, which, as we note before, is equivalent to a comma b under our equivalence relation. Therefore, the equivalence class of 1 comma 1 in our quotient space z satisfies the group identity law for this set, and we note that a comma b plus b comma a is equal to a plus b comma a plus b comma a plus b by rearranging terms, which is equivalent to 1 comma 1. So the equivalence class of b comma a in the quotient space acts as the additive inverse of the equivalence class of A comma B, so Z is a well-defined ring. With this ring structure created, we can now consider some mappings and some relationships between the natural numbers and our integers as we've constructed them. Namely, if we consider some mapping phi from the natural numbers to the integers that associates any n with its equivalence class in terms of the pair n plus 1 comma 1, which is an element of the Cartesian product of the natural numbers with itself, then since if we note that m plus 1 comma 1 is equivalent to n plus 1 comma 1, if m is equal to n by applying cancellation on m plus 2 comma n plus 2, then we see that the mapping phi identifies the natural numbers with a subset phi of n within the natural numbers. Furthermore, we have that phi of the addition of two elements is the equivalence class of this complicated pair m plus n plus 1 comma 1, which is equivalent to m plus n plus 1 comma 1 plus 1, which we then group these two terms together and the outer terms together, and we get that this is m plus 1 comma 1 plus n plus 1 comma 1. So we see that phi respects addition on the integers, namely that phi of m is equal to phi of n. So, and then we will note the same thing applies for multiplication in the sense that phi of m times n is the equivalence class of m times n plus 1 comma 1, while phi of m times phi of n is the equivalence class of this term times this term, which we multiply out and rearrange. And we get this term, which is equivalent to mn plus 1. So we get that phi of m times n is equal to phi of m times phi of n. Thus, we will note that phi is an embedding, namely that we send a set to a subset to a larger, or as a subset of a larger set from the natural numbers to the integers. We see that the algebraic operations Rn are just a restriction of the algebraic operations on Z. So Z is an extension on the set with its algebraic operations into a ring. Another way of phrasing that is that the sets plus and times in N are well defined on Z. So we use those operations as the operations of plus and times on Z, and those operations will make Z into a ring. To note what elements are contained in the larger set Z, which are not contained in the subset N, it is clear that any pair m comma n is equivalent to either 1 comma 1 or k plus 1 comma 1 or 1 comma k plus 1, where k is an n. But the equivalence class of k plus 1 comma 1 is in the image of phi of n of the natural number k, while the element 1 comma 1 we've noticed is the additive identity of Z, but is not contained in phi of n. Namely, you can think of the fact that 1 comma 1 will act as 0, and there is no 0 element in n, therefore phi of n is not 0 is not in phi of n, because there's no element 0 there's no element 0 within n, which phi can send to 0. We will then finally note that the 1 comma k plus 1 equivalence class for any k is the inverse phi of k, and is not contained in phi of n, so the only elements of n that are not contained in the image phi of n are precisely those elements which are inverses of the image of phi of n. Namely, those elements need to extend the natural numbers into a ring. In that sense, we can consider the integers as the disjoint union, n union with 1, union with minus n. And whenever m comma n are in the Cartesian product, then m comma n are equivalent to m plus 1 plus 1, comma n plus 1 plus 1, which is the sum of m plus 1 and n plus 1, which is merely phi of m minus phi of n. So the elements of the ring Z can be identified with the difference elements in the image of phi of Z of the natural numbers within the ring Z. Another way of considering that is that if we consider how we originally defined this operation, making pairs of elements out of two integers, we consider that a comma b, we will associate that with the element a minus b. Namely that for two real numbers a and b, a comma b is the integer element a minus b. And that will make a lot of this more clear if you're feeling confused about it. For instance, the idea that n plus 1 comma 1 is equivalent to n is the idea that n plus 1 minus 1 is just n. So all elements of the form n plus k comma k are equivalent to the element n. And we see that that's identified by our rule that pairs of natural numbers, a comma b, are equivalent to one another if the alternating sums are valid, namely that this operation is satisfied. We see that if you consider this left element to be a1 minus b1 and the right element to be a2 minus b2, then you can add b2 and b1 to both sides and generate this rule. This will make a lot of this explanation easier if you felt confused about it. With that, we've successfully extended the natural numbers into a ring, which we call the integers. So we will spend some time considering some more ideas within rings, namely those of ordered rings and polynomial rings. Thank you.